Good day. Our practical today is volumetric analysis. The method commonly used during the interaction between an acid and a base is known as titration. Titration is a technique used in determining the volume of acid that will completely react with a fixed volume of base. It can also be used to determine the concentration of an acid or a base. The apparatus that commonly used for acid-base titration are Whittle stand, burette, conical flask, wash bottle, funnel, pipette, white type, and volumetric flask. In acid-base titration, a suitable indicator is employed to determine the endpoint of neutralization. This can be a methyl-orange, methyl-red, or phenolphthalein, depending on the strength of the acid and the strength of the base. For example, any of these indicators, methyl-orange, methyl-red, or phenolphthalein, is suitable for the neutralization involving strong acid and strong base. Methyl-orange or methyl-red is suitable for the neutralization between a strong acid and a weak base. For example, the neutralization involving the following: white phenolphthalein indicator is suitable for the neutralization between a weak acid and a strong base, such as weak acetic acid and strong sodium hydroxide. The endpoint for an acid-base titration is the point at which a titration is complete, usually marked by the change in color of an indicator. Procedures for acid-base titration: wash and rinse the titration apparatus with dilute water. Wash and rinse the titration apparatus with distilled water. Rinse the burette in the acid solution, labeled AN, and a pipette with the base solution, labeled BN. Fill the burette with the acid to reach the main viscous level at point 0. The solution of acid in the burette is called the titrant. Pipette the base into the conical flask and add 2 to 3 drops of indicator. The solution in the conical flask into which an indicator is added is called a titrant. Place the conical flask in the white type, which is underneath the burette, and begin the titration. It is good to observe the following precautions during titration. Do not place the conical flask underneath the burette while filling with the acid solution. Remove the funnel from the burette before titrating. Carry out your reading at meniscus and eye level. Rinse the conical flask with distilled water before carrying out the next titration. Do not look at the burette while titrating the titrant in the conical flask in order to have an excellent endpoint and a concomitant value of plus or minus 0.2 cm3. Table of values. The table should be prepared before starting the titration, and the features are burette reading, final reading, initial reading, volume of acid used, rough, first titer, second titer, third titer. The first and the foremost titration is regarded as rough. It must be carefully carried out in order to determine the endpoint range. When the initial reading is subtracted from the final reading, the volume of acid obtained is called the titer value, which is the volume of the acid used. It is good to note the following: burette reading must be recorded to 2 decimal places. Units must be placed, and the acceptable unit is centimeter cube. The indicator and the volume of pipette used must be stated. Values must not be shaded. Calculations must be correctly evaluated. Writing must be in ink. the average total volume of acid used must be from at least 2 concordant titer values. The next aspect in acid-base titration is the calculations and mathematical definition of some terms in volumetric analysis. You need to commit the following mathematical definitions to memory for competencies during practical test. The first is mole. The mole represents the amount of substance that contains 6.02 times 10 raised to the power 23 particles. Mole can be expressed in two ways. A. Mole is equal to mass over molar mass. B. Mole is equal to concentration times volume, where C is concentration in mole per dm cube, V is volume in dm cube. Remember, 1 dm cube is equivalent to 1000 centimeter cube. Question: what is the molar concentration of 0.125 mole of hydrochloric acid in 250 centimeter cube? This can be calculated by applying the mole formula Cv and substituting the parameters. Mind you, you need to convert 250 centimeter cube to dm cube, and this can be done by simply dividing 250 by 1000. Here mole is equal to Cv and the molar concentration is 0.500 mole per dm cube. The next mathematical definition is a standard solution. A standard solution is a solution of known concentration, and it can be expressed in two ways. The mathematical relationship between mass concentration and molar concentration is given by mass concentration is equal to molar concentration times molar mass. Note, the subject of the formula is employed when solving for any of the three quantities. Question: A is a solution of hydrochloric acid containing 5.0 gram per dm cube. Calculate the concentration of A in mole per dm cube. Solution: we apply our formula, which is mass concentration is equal to molar concentration times molar mass. First and foremost, you'll find the molar mass of hydrochloric acid. Here, the molar mass of hydrochloric acid is 36.5 gram per mole. Now, substitute this value and the mass concentration in gram per dm cube into our formula. We obtain the molar concentration of A to be 0.137 mole per dm cube. Question: B is a solution containing 1.4 gram of potassium hydroxide per 250 centimeter cube of solution. Calculate the concentration of B in gram per dm cube. Ask yourself this question: if 1.4 gram is contained in 250 centimeter cube of distilled water, then how many gram will be contained in 1000 centimeter cube of distilled water? By using cross multiplication method, we obtain the concentration of B to be 5.6 gram per dm cube. Next, stoichiometric formula. The stoichiometric ratio of acid to base is given by CAVA over CBVB is equal to NA over NB. where Ca and Cb are concentration of acid and base in mole per dm³ respectively. Va and Vb are the volumes of acid and base respectively, and Na over Nb is the stoichiometric mole ratio of acid and base. Example: hydrochloric acid and sodium triacylcarbonate react in the following way. Here, the stoichiometric ratio of acid to base is 2:1. Consider the following reaction equation. What is the volume of 0.400 mole per dm³ hydrochloric acid that will neutralize 25 cm³ of 0.2 mole per dm³ sodium triacylcarbonate 4? Here, the parameters given are Ca is equal to 0.4 mole per dm³, Va is unknown, Cb is 0.2, Vb is 25 cm³, Na is 2, Nb is 1. Applying the stoichiometric formula and substituting the parameter, we obtain the value of our Va here to be 25 cm³. The dilution formula is given by C1 V1 is equal to C2 V2, where C1 is initial concentration, C2 is final concentration, V1 initial volume, V2 is the final volume. Note, C1 and C2 are expressed in mole per dm³. An acid-base titration can be used to work out the following. 1. The percentage purity of an acid or a base. The formula for percentage purity is as follows. Percentage purity is equal to mass of pure substance over mass of impure substance times 100%. Number of particles. The number of particles can be obtained using Avogadro's constant, K. K is equal to N, which is number of particles, over A, the basis of an acid, times M, which is molarity of acid, where A is the basicity of the acid, M is the molarity of the acid, and N is the number of particles. Question. A is a solution of hydrogen tetrasulfate 6 acid containing 5.0 gram per dm³. B is a solution of impure potassium hydroxide containing 6.50 gram per dm³. From the table of values of Faber etodo, the average volume of acid that completely neutralized 25 cm³ portion of the base is 22.40 cm³. A question. Calculate the concentration of A in mole per dm³. To calculate the concentration of A in mole per dm³, we apply our formula. Mass concentration is equal to molar concentration times molar mass. First and foremost, find the molar mass of hydrogen tetrasulfate 6 acid, and here the molar mass of hydrogen tetrasulfate 6 acid is 98 gram per mole. Substitute this value into our formula. We obtain the molar concentration of A to be 0.510 mole per dm³. Our concentration of B in mole per dm³, we use our stoichiometric formula, which is CAVA over CBVB is equal to Na over Nb, where our Na is 1 and our Nb is 2 from the equation. By substituting our values into this formula, we obtain the concentration of B to be 0.0914 mole per dmK. The next is the percentage purity of potassium hydroxide in B. Hint: first determine the molar mass of pure potassium hydroxide in B. The mass concentration here is not 6.50 gram per dmK because it is impure. Using the formula, mass concentration is equal to molar concentration times molar mass. We first of all find the molar mass of potassium hydroxide, and here the molar mass of potassium hydroxide is 56 gram per mole. Therefore, substituting our value here, we obtain the mass concentration to be 5.5 gram per dmK. Therefore, the percentage purity is equal to mass of pure potassium hydroxide over mass of impure potassium hydroxide times 100%. Our value here is 85.23%. The next is the number of hydrogen ions. We can get this by using the Avogadro's constant. N is equal to the number of particles over the basis of the acid times molarity. Here our final result, here the number of particles is 6.143 times 10 raised to the power 22. Theory of particle. Determination of number of water molecule in a substance. Question: determination of number of water molecule in a substance. Question: solution A is 0.100 mole per dmK, solution of hydrochloric acid. Solution B is 11.15 gram of hydrated sodium tricarbonates 4 per dm³ of solution. 25 cm³ of solution B required 20.8 cm³ for neutralization. From the information given above, calculate the concentration of solution B in mole per dm³. Molar mass of B, the value of X. Solution. To find the concentration of B in mole per dmK, we apply our stoichiometric formula. Then substituting our parameter into the stoichiometric formula, and we obtain the molar concentration of Cb to be 0.0416 mole per dmK. To find the molar mass of B, we use our formula, which is mass concentration is equal to molar concentration times molar mass. Now, substituting our values into this formula, we obtain the molar mass of B to be 268.03 gram per mole. The value of X. The value of X here, our X is approximately 9.0. Here our value of X is 9, which is the number of water molecule in the hydrated compound.